Hi everyone. Today I want to continue from the previous video, which is the proof of the problems concerning triangular numbers. So we know that these numbers 1, 3, 6, 10, 15, 21, 28, all the way and so on. These are triangular numbers. Okay? Right? We know that these are triangular numbers. It consists of one for the first number, and the second one you have to add it by 2, so it's become 3, right? Add this 2 dot, and then 6, 10. Okay, 6 plus 3 plus 4, so you have 10, plus 5, so that you have 15, plus 6, so you have 21, plus 7, you have 28. Okay, next is to plus, okay, plus 7 and plus 8, right? You have 36 and so on. And we know that if, okay, tk, right? If tk is the n triangular number, so we know that t of n turns out to be 1 plus 2 plus 3 all the way to n, alright? Which is n over 2 times n plus 1. So which is the sum of consecutive number from 1 to n. But now, before we continue with the proof, let's talk about Pell's equation. So Pell's equation is the Diophantine equation of this form. Okay? X squared minus ny squared equals 1. What is n? N is a non-negative square. Okay? Non-negative square integer. And these equations, as long as n is a non-negative square integer, the solutions x and y are integers. And there are infinitely many integer solutions. Okay? So if you have the equation in this form, x squared minus n y squared equals 1, there will be, and n is a non-square integer. So this equation will have infinitely many solutions. Okay? For example, x squared minus, let's pick one of the non-square integer, 2 y squared equal 1. This equation satisfies Pell equations and it has infinitely many integer solutions. And x squared minus 3 is non-square, it will have infinitely many non-integer solutions. And x squared minus, let's say, okay, 120 is a non-square, right? Okay, so these has infinitely many integer solutions. Alright, but if you have x squared minus 9y squared equals 1, these equations, for this equation, it might have integer solutions, but they will be finite. It might have finite, or it doesn't have. Okay, so it's not satisfying Pell equations. Okay, this is not a Pell equation. It might have finite integer solution. Okay, finite number of integer solutions or do not have solutions. Okay, but it depends on the value of x and y. But if you take a look at this equation, it looks like we have the graph of parabola. Wait, sorry, the graph of hyperbola. Okay, so there will be solutions, but there may be finite. Sorry, there may be finite number of integer solutions. Okay, it might be. I said maybe. I'm not sure. All right, but Pell equations, which is this one, and n must be non-square integer. This equation will has infinitely many integer solutions. Okay, now let's take a look at the proof here. Okay, so there are infinitely many triangular numbers which are perfect square. Okay, so let's list triangular numbers. We have 1, 3, plus 3, 6, plus next number, plus 4, right? 10, plus 5, okay. Plus 6, 21, plus 7, 28, plus 8, 36, plus 9, 45, plus 10, 55, plus 11, 66, plus 12, 78, plus 13, 91, plus 14, 105, plus 15, 120, all the way and so on. Okay, but we found that 1 is a perfect square, right? I don't know where is another perfect square, but we have to show that there are infinitely many triangular numbers which are perfect square. All right, so what can we do with this? Okay, so let's prove it. And I can prove this by using Pell equations. Proof by Pell equations. So we let TK, okay, be a triangular number. All right, for any integer n. Then what happened to T of n? T of n is going to be the sum of consecutive number from 1 to the n. Okay, so it's going to be 1 plus 2 plus 3 all the way to n, which is n times n plus 1 over 2. All right. Now, to show that this triangular number has a perfect square and infinitely many perfect square, I have to assume that there, okay, exists a triangular number, let's say Tm, okay, let's say Tm, which is a perfect square. So what happened if Tm is a perfect square? So you must be able to write Tm as a square number, right? So you must be able to find, let's say, positive integer k, okay, such that Tm equal k square, okay, and Tm is a triangular number, so 3m turns out to be m times m plus 1 over 2 equal squared. Okay, equal k squared. From now on, to show that triangular number Tm has infinitely perfect square. Okay, to show that triangular numbers m, okay, I should say this, to show that there are infinitely many triangular numbers which is a perfect square, we have to show that this equation has infinitely many solutions, right? Okay, so try to show that this equation has infinitely many solutions. So what can we do with this? I want to eliminate number 2. So I want to multiply it by a both sides. So it's going to be 8m times m plus 1 over 2, which is 8k. Then it turns out to be 4m times m plus 1, which is 8k squared. Okay? And this to be 4m. So it turns out to be 4m squared plus 4m. Okay? Equal to 8k squared. I add one both sides. Add one both sides so that the left hand side become a complete square, right? Okay, then it turns out to be 2m plus 1 square equals 8k square plus 1. For the Pell equation, we're gonna have x squared minus ny squared equals 1, right? Where n is a non-square integer. So what can we do with this? So we have number 1 right here, and we have 8k squared right here. So we're gonna move 8k to the left side. So it turns out to be 2m plus 1 square minus 8k square equals 1. And then it turns out to be 2m plus 1 square minus 2 times 4k square. And 4k square, what is it? We can write it as 2k square equals 1. This is minus. Okay. So, right now we have 2m plus 1 square and 2k. Okay. So what do we mean by this? This means that 2m squared plus 1 is an odd number. 2k is an odd number, right? And 2 is a non-perfect square. All right, so since, okay, m is an integer, okay, is a positive integer, that is m. This means that 2m plus 1. So 2m plus 1 satisfies the definition of odd numbers, right? Is an odd number. Okay, so we can write, we can say that there exists an integer n such that x equal 2m plus 1. And 2k, the same goes with 2k. 2k is an even number. Okay, so there must exist n such that positive integer n such that since k is an integer, so 2k is an even number. Okay, so there exists, right? Let's say y, okay, y which is an integer such that y equal to k. Okay, so this equation, let's say this is equation 1. What does it become? Okay, so 1 becomes x squared, right? Now it's x minus 2y squared equals 1. Okay? Which is a Pell equation, right? Which is a Pell equation. Okay? So there will be infinitely many solutions. Okay? Hence there are infinitely many integer solutions x and y. If you can find x and y, x equal to 2m plus 1 and y equal to 2k, you must be able to find infinitely many m and k. Okay? Right? So, hence, so equation 1, okay, equation 1 will has infinitely many integer solution 2. Alright? Okay, so we proved this statement already. Okay? We have proved this statement already. We have proved that there are infinitely many triangular numbers which are perfect square.